Test, test, test. Okay, let me know if you can hear. Okay, it's just a heads up. There's about 15 or 20 second delay between me actually saying stuff and you hearing it. So responsiveness is going to be a bit further back from where it would usually be. So we're going to take a look at this question 4 very, very quickly, and then we'll go on to the proof by induction. Hopefully Zoom will be working tomorrow. If not, we'll be using this again, but hopefully it might be a bit better. Right, so question 4 is wrong. Okay, so we're just doing part 2 and part 3. So the first one, after how many payments will the loan be cleared, we can do one of two things. We can either use the ax by 1 minus x to the power of t all over 1 minus x version of it, where we use the p 1 minus x over x by 1 minus x to the power of t is equal to a, using our 150,000 for p, and for x we need to figure out what that is, don't we? So we use 1.01825 to the power of 1 over 12. Yep. That's equal to something. That's equal to something. We divide the something into 1, and we'll get from that 0.9934 ... And the answer we get to this, we'll store that in the calculator as x. Because it's present values we're dealing with, and this time we have to do the 1 divided by it rather than just using the regular interest. And we're going to fiddle into our formula now. P is 150,000 is equal to 1127 x bracket 1 minus x to the power of t all over 1 minus x. And multiplying across, we'll get 150,000 bracket 1 minus x all over 1127x is equal to 1 minus x to the power of t. If we calculate out the left-hand side here, the 150,000 divided by etc., this all turns into 0.882 something something something. That's equal to our 1 minus x to the power of t. So we have x to the power of t is equal to 1 minus 0.882, and so on. You get x to the power of t is equal to 0.11784, and so on. And so t is equal to log to the base x of 0.11784 dot dot dot, which gives us t is equal to 324 months. So I'll pause here for a moment and you can let me know if there's any part of that you'd like clarified. Okay, so Jill, the answer that we get out of the calculator there for the 1 to the power of, or 1.01825 to the power of 1 over 12, we type 1 divided by the answer to that into the calculator, and according to what I did yesterday, it gives you back 0.9934 and then a load more decimals after that as well. So the something is just the answer to the 1.01825 to the power of 1 over 12. Okay, the part 3 was the real challenge to this one. So after 5 years of repaying the loan, they make a lump sum payment of €40,000. How long will it take to repay the loan after this payment? So what I want for this is, because all of the present values of the repayments have to add up to the original 150,000, so all the present values add up to the 150,000. Well, the present value of not 150,000, but the present value of €40,000 in 5 years' time is 40,000 over 1.0825 to the power of 5, which is equal to 26910.42. Okay, so we're now going to knock that off of the 150,000. That'll give us 123,089.58. And now the present values of the monthly repayments add to 123,089.58. And we're going to put that into the formula that we were using above again. So the value of x hasn't changed. The only thing that's different is that it's starting with a 123,089.58 is equal to 1127x by 1 minus x to the power of t all over 1 minus x. So 123,089.58 by 1 minus x all over 1127x is equal to 1 minus x to the power of t. The left hand side here works out as 0.7238985 and then a bunch more numbers after that. That's our 1 minus x to the power of t. So x to the power of t is 1 minus 0.7238985 dot dot dot. And t is equal to log to the base x of 1 minus that number and we get t is equal to 195 months. Now this isn't the final answer yet, because the question was how much longer after they pay back the €40,000 how much longer after that will it take them to fully pay it back. So we have to take the 5 years off of that, so take away the 60 months and you get 135 months. Again, I'll pause there. I assume there will be a lot of questions about this one because it's not obvious. The power of 5 there is coming from the fact that it's 5 years into it, and the reason we know to put it over the interest is because we're adding up all of the present values, and present values is always dividing by the interest. The 60 months at the end is coming from the fact that it's 195 months from the day that the loan is taken out. The question was asked, how many months after the 40,000 is paid back does it take after that? So we're going 60 months in, and we're saying that because it took 195 months in total, it was 135 months after that 60. Because we're looking at how many months it is after the 5-year mark rather than after the day the loan was taken out. The reason we knew that, Jill, was because that's always the formula that we're using when we're looking at either payments into a fund or payments out of a fund. So anything in financial maths we will be able to use that formula for, as long as it's going into that whole geometric series area of it. That is not just kind of a straightforward calculate the interest or see how much a particular thing grows to after a number of years. If you're going into gradual payments out of an account or gradual payments into an account, then we'll always be using that formula or the amortization one. Alright, so I'm going to go on ahead to the new area that we'll probably be looking at for most of this week, which is proof by induction. Now there's 4 stages to doing something in a proof by induction, so we're just going to look at the 4 stages first, and then we're going to look at a couple of examples of questions using it. So the 4 stages are, first of all, we have to prove that the statement is true for n equals 1. In other words, there's going to be some sort of n or x, something like that in our equation. Generally it is n. And we need to prove that if we fill in n into the formula that we're given, that the 2 sides of our equals balance out. That it is a solution. After we've proved that that works, it won't always be 1 either, but it'll be 1 for now, we're going to make an assumption that statement is true for n equals k. So we're going to assume that if we fill in k into the formula, that it's going to be true still. Once we have that done, we're going to prove that the statement is true if we fill in k plus 1 instead of k, under the assumption that it was true for k. And the final step, and this is where everything kind of comes together, is that because we knew it was true for the first step, and we proved that if it's true for one step, it's true for the step after that. That means it'll also be true for n equals 2. It'll also be true for n equals 3 because it was for n equals 2. Being true for n equals 3 makes it true for n equals 4, and that's just going to keep going on. So it means it is true for every natural number. It doesn't make a ton of sense until you actually start looking at questions for it, so I wouldn't focus too much on understanding what all of that says. So first question on proof by induction. I can't remember the page this is on, but I'll add it on afterwards. So prove that if you add on all of the even numbers to a certain point, that's the same as multiplying together n by n plus 1. So the n part here is just telling us how far into it we're going. And we just want to prove this formula. So step 1 is to prove it for n equals 1. So we're just adding up the first even number. That means that we're doing 2 on the left hand side. And we want to know, is 2 equal to 1, or 2 bracket 1 equal to 1 bracket 1 plus 1. So we're taking the right hand side here and replacing our n's with 1s. 2 by 1 is 2. 1 plus 1 is 2. 2 is equal to 2, yes. And that means it's true for n equals 1. Step 2. Is that we're going to assume that it's true for n equals k. So that means that 2 plus 4 plus 6 plus all the way up to 2k is equal to k bracket k plus 1. So all of the even numbers from 2 up to 2k is the same as adding together k squared plus k. We're not going to do anything more than that. We're just going to assume that that is the case. Step 3 is that we're going to prove it's true for n equals k plus 1. So this is 2 plus 4 plus 6 plus all the way up to 2k plus 2 bracket k plus 1 is equal to k plus 1 multiplied by k plus 1 plus 1. Now a lot of the time with these, we need to make some kind of connection between step 2 and what we have here in step 3. The connection here is that all of the numbers there in that red bracket, those are equal to, from the previous part, k squared plus k. Plus 2 bracket k plus 1 is equal to k plus 1 by k plus 2. And if we multiply this out, we've got k squared plus k plus 2k plus 2 is equal to k squared plus k plus 2k plus 2. If we multiply out the two brackets on the right hand side, and then we've got k squared plus 3k plus 2 is equal to k squared plus 3k plus 2. Which means that it's true for n equals k plus 1 if it's true for n equals k. And finally, what we need to kind of understand ourselves here is that since it was true for 1, and we've proved that if it's true for a certain number, it's true for a number that's 1 bigger than it, that means it has to be true for 2 as well. And since it was true for 2, which we just shown, that means it's also true for 3. And since it's true for 3, it'll be true for 4. Because it's true for 4, it'll be true for 5. Because it's true for 5, it'll be true for 6. And that'll keep on going forever. So finally, since it was true for n equals 1, it's true for every natural number. Right, let me know if there's any part of that one that you'd like looked back at. It's very, very unlikely to happen, Ava. Now the thing with it is that it only works for kind of discrete proofs, so it has to go in jumps of 1. The only thing they could do is make it go in like jumps of a half, and you have to turn it into jumps of 1 based off of that, but it's very, very unlikely to happen. As for y, it's k plus 1 plus 1, and the formula up above was k by k plus 1, so we replaced our n by n plus 1. So we replace the n's with k plus 1's. So the first n becomes k plus 1, and the n plus 1 becomes k plus 1 plus 1. So the 2 bracket k plus 1 is going to, in fact, we're adding up even numbers. So it's starting off, the 2 is 2 bracket 1, 4 is 2 bracket 2, 6 is 2 bracket 3. That continues on up until we get to 2 bracket k, and we've just written that as 2k. And the 2 bracket k plus 1 is the one that comes after that. We just haven't, we could have written it out as 2k plus 2, but it's just easier for managing at this stage if we put it in as the 2 bracket k plus 1. It's because we're multiplying 2 by the number that we're adding in. Right. So, second example we'll take a look at is number 2. So it's showed that if we keep on adding up, and it's very, very important here to look at the last term, 3n minus 2. So all of these numbers are 3 by something minus 2. So the first one is 3 by 1, which is 3 minus 2, that's the one we got there. The second one is 3 by 2 is 6 minus 2 is 4. Then 3 by 3 is 9 minus 2 is 7. So all of these numbers are 3n plus 2's. So we could write this out as the sum for n equals 1 to n of 3n minus 2. And again, starts off the exact same way. Prove that it's true for n equals 1. Means that we want to prove that 3 by 1 minus 2 is a half of 3 by 1 minus 1. 3 by 1 is 3, minus 2 is equal to a half of 3 minus 1. 1 is equal to a half of 2, which 1 is equal to 1, meaning that it's true for n equals 1. Step 2. So we're going to assume it's true for n equals k. So 1 plus 4 plus 7 plus all the way up to 3k minus 2 is equal to a half of 3k minus 1. So there should be a k over 2 outside. Step 3. Is to prove that it's true for n equal to k plus 1. So 1 plus 4 plus 7 plus all the way up to 3k minus 2 plus 3 by k plus 1 minus 2 is equal to k plus 1 over 2 by 3 bracket k plus 1 minus 1. Now again, just like in the previous one, we know that the first few terms there all came out to k over 2 by 3k minus 1 plus, and if we multiply out that second one, we get 3k plus 3 minus 2 is equal to k plus 1 over 2 by 3k plus 3 minus 1. And so here we've got k over 2 by 3k minus 1 plus 3k minus 1 is equal to k plus 1 over 2 by 3k plus 2. Yes, this one should have been, in fact, a plus 1 here. I get a very distinct feeling I've gone wrong somewhere here, but we'll keep going just in case. If we multiply this out, we get 3k squared over 2 minus k over 2 plus 3k over 2 plus 1 is equal to, if we multiply the right hand side out, we get 3k squared over 2 plus 3k over 2 plus 2k over 2 plus 2 over 2. All of this goes together now. We've got 3k squared over 2 plus, that shouldn't have been a 3k over 2 here actually, that should just have been a 3k. So 3k minus k over 2 is 5k over 2 plus 1. It's equal to 3k squared over 2 plus 5k over 2 plus 1. And both sides there match up. That means it's true for n equals k plus 1. If it's true for n equals k, therefore, since it was true for n equals 1, it has to be true for all of the natural numbers, by the same reason as last time. Being true for 1 makes it true for 2, being true for 2 makes it true for 3, and so on. And 5k over 2 on the left is that 3k is the same as 6k over 2, and we're subtracting k over 2 from that. So the 6 minus the 1 gives us the 5k over 2. Okay, we can take a look at one last one of these before we finish up. And it may take a little while to get the questions up for today, purely because I'm going to have to go straight into fifth years after this. I won't have any time in between. So what's important here with question 3 is that these numbers here are not 1.2. The dot in between means 1 multiplied by 2, or 1 times 2. So it's 1 times 2 plus 2 times 3 plus 3 times 4 plus 4 times 5, etc. And it's given to us over here as the sum of all the n by n plus 1s. Again, step 1 is to prove that it's true for n equals 1. So 1 bracket 1 plus 1 is equal to 1 over 3 bracket 1 plus 1 bracket 1 plus 2. So 1 bracket 2 is equal to 1 over 3 bracket 2 bracket 3. And 2 is equal to 1 over 3 by 6. Therefore, it's true for n equals 1. Step 2 is to assume that it's true for n equals k. So that means that 1 times 2 plus 2 times 3 plus 3 times 4 up as far as k by k plus 1 is equal to k over 3 by k plus 1 by k plus 2. Step 3. Let's prove that it's true for n equals k plus 1. So 1 times 2 plus 2 times 3 plus 3 times 4 all the way up to k by k plus 1 plus k plus 1 by k plus 2. That's equal to k plus 1 over 3 by k plus 2 by k plus 3. Now the right hand side here is purely just the same as the previous one, but we're adding 1 onto every term. So instead of writing it out as k plus 1 over 3 by k plus 1 plus 1 by k plus 1 plus 2, just putting it in as the k plus 2 by k plus 3. Now the red part here, we know that that's the same as k over 3 by k plus 1 by k plus 2 plus k plus 1 by k plus 2 and the easiest way in fact to do this one is write it as k over 3 by k plus 1 by k plus 2, and I'm just going to write in next to this part here a 3 over 3. So 3 over 3 is the same as 1, so that doesn't change any values. However, now we've got similar fractions on the two of these, so all that we need to do is add together the front two parts here, because the parts following them in both of those are just k plus 1 by k plus 2. So we've got k plus 3 over 3 by k plus 1 by k plus 2 is equal to k plus 1 over 3 by k plus 2 by k plus 3. Okay, and the two sides there do match up. They're in different orders, but multiplication is commutative, so the order that they're in doesn't actually change any values. And finally, to finish it up, it's true for n is equal to k plus 1 if it's true for n equals k, and since it was true for n equals 1, it has to be true for every natural number. And it's also equally valid to have gone and multiplied out everything up above, but sometimes there's these little tricks you can see where you just find a way to avoid doing that, because multiplying all of those out, it's fairly likely that a mistake's going to happen somewhere. So if you can see something there, that if you can notice that there's all these k plus 1s, k plus 2s showing up in every term, you can kind of know at that stage that you only really need to focus on what else is there, and you might be able to make some correlation between those. Let me know if there's any part of that you'd like clarified, and if not, we will finish up there. And apologies again about Zoom not working this morning. Hopefully tomorrow it'll be back to normal. And just very quickly as well, with the exam question I gave you to do, I've only gotten 5 of them back. So if you haven't gotten it done, please do try to do it, because it's important to see how we're actually managing and how we're dealing with exam questions.